If you had an experience of studying chemistry or physics, you might have had a chance to come across Heisenberg's uncertainty principle at least once. And I'm going to tell you about this principle from the process of its creation to its effect on science. Before Heisenberg's uncertainty principle was presented, scientists thought that an electron moves in a fixed orbit and could determine the exact position and velocity. Just like this model that you might have seen a lot. And this is called classical mechanics, where scientists take a deterministic attitude. But Heisenberg's uncertainty principle, which states both the position and the momentum of a particle cannot be precisely measured at the same time, proved this to be wrong. This is called quantum mechanics, where scientists take a probabilistic attitude. To start with, you need to know how Heisenberg's principle emerged. Niels Bohr suggested an atomic model where electrons orbit around a specific track. However, the model that Niels Bohr suggested did not apply to elements with more than 2 electrons. It could not explain the spectrum of the elements. So, there needed to be a new atomic model, and that's how Heisenberg's uncertainty principle appeared. To explain Heisenberg's principle, let's take a baseball for example. To measure the position and the momentum of a thrown baseball, a photon needs to hit the ball for us to see, then to measure the ball. Here, the mass and the power of the photon is so small that it does not affect the momentum and the motion direction of the baseball. However, unlike baseball, an electron is very light. And a crash with a photon can have an effect on the electron's location and momentum. And this is where Heisenberg's uncertainty principle comes into play. So, in a microscopic world, in order to measure position of an electron more accurately, you need a photon with shorter wavelength. But wavelength is in inverse proportion due to this equation, E equals hc divided by lambda, where lambda here equals the wavelength. So shorter the wavelength, bigger the energy. Therefore, using a photon with shorter wavelength to measure the position of the electron more accurately will result in a bigger change in momentum due to larger energy of a photon. When expressed in the equation, it looks like this. Delta x times delta p is bigger or equal than h divided by 2 pi, where delta x equals to uncertainty in position, delta p, uncertainty in momentum, and h divided by 2 pi is a fixed number. So higher the probability of a position, lower the probability of a momentum, and vice versa. And due to this principle, the position and the momentum of an electron had to be expressed in a probability. As I said before, in the microscopic world, the position of an electron cannot be determined. And that's because electrons have both the traits of particle and a wave. We can see this through a simple experiment. If electrons are shot through a barrier with a single slit, an electron is detected at a specific location, just like a particle. However, if this experiment is done repeatedly, it shows a repeated pattern which shows the characteristic of wave. And the wave nature means an electron moving, not staying in a fixed position. So Erwin Schrödinger came up with a wave function which took wave nature into consideration. And this wave function makes it possible to measure the possibility of electrons' position, which led to invention of an orbital. So, orbital is an area where there is a high chance of finding an electron. In the end, the Heisenberg's uncertainty principle played a big role in the emergence of quantum mechanics, which takes a critical part in today's world. Just like this, today's world is just a huge game of chance.